right, good morning, everybody. So we're on the lecture deck number 16. So this is equals, hashCode, and compareTo. Now in the lecture slides, it starts off by talking about equals using a different approach compared to what we did in class in the previous lecture. I'm going to skip over this part for now, and I'm going to come back to this when we talk about inheritance. So if you're following along in the lecture slides, I'm going to skip past the first 12 slides. So I'm going to jump right into the hashCode part. The reason for jumping ahead is that the second form of equals isn't useful for us at the time being. It will become useful for us when we talk about inheritance. Instead, I want to talk about this method called hashCode. So there's a rule in Java that says if you replace the implementation of equals in your class, then you must also replace the implementation of hashCode in your class, which is it's a strange requirement because hashCode is not a method that a normal programmer will ever use directly. Instead, hashCode is a method that the hash containers need to work correctly. So the hash containers in Java are the things called hashset and hashmap, and anything else that has the word, and many of the other classes that have the word hash in their name. If you don't replace the implementation of hashCode when you replace equals, then things like hashset and hashmap, they don't work properly. Okay, so remember for our point2 class, we've overridden equals. So we have 2 points are equal if they have the same x and y coordinates. We haven't looked at hashCode at all, so we haven't replaced the hashCode method yet. If I make a point p, its coordinates are 1 and minus 2. Right? I can make a hash set, and I can add p to the hash set. Right? So I can put the point into the hash set. If I ask the set, right, does the hash set contain the point p? Right, then you get the answer true, which is good because I just put it in on the previous line. Right? On the previous line, I added the point p to the set. Now, if I make a new point q that's equal to p, right? So it has the same coordinates, right? 1 and minus 2, 1 and minus 2. Right? So I make a new point q that's equal to p, and then I ask the hash set, do you contain the point q? Right? The hash set says false. It does not. Right? And if you look at the documentation for hashset says it returns true if it can find an element that's equal to the one that you're asking for. Right? Well, q is clearly equal to p, right? Because they have the same coordinates. But the hashset thinks that q is not in the hashset. Right? So now you're in the situation where the hashset collection does not work properly because you forgot to include the hashCode method in your class. Right. Now, why is this happening? So to understand why this is happening, you have to understand how searching works. Right. So suppose you have a list of point2 objects. Right. If you wanted to know, does this list contain a point, right, you would probably just call the contains method on the list. Right. If you didn't know that contains existed, though, you would write a loop. Right. So you would write a method that looks something like this. Right. I would like to know, does the list called points, does it have a point p inside the list? Right, true or false? Right, to implement this, you would just write a loop. Right, so for each point in points, right, so in other words, for each point in this list, right, if an element of the list is equal to the point p that you're looking for, you can return true. Right, so you just search all the elements in the list. As soon as you find one that's equal to p, you return true, right? So you're using equals here to determine equality. If you search all of the points in the list and you don't find one that's equal to p, you return false, right? Hopefully you can all do that, right? That's just a straightforward sequential or linear search, right? It's called linear search because the amount of time you need to search the list is proportional to the length of the list. Right? So doubling the length of the list doubles the amount of searching that you need to do. Right? If you're going to do the complexity analysis on this, right, you would say, well, what's the best case complexity? Well, the best case complexity is the list has, the first element of the list is equal to the one you're searching for, right? So that's exactly one call the equals, right? So in the best case, this is O1 time. However, in the worst case, the thing you're looking for is not in the list, or it's the last element in the list, right? If there's n elements in the list, that's n calls to equals, right? So that's big O of n. On average, though, assuming the thing is inside the list, then you're going to look at roughly half of the elements in the list before you find the thing that you're looking for, right? On average. So if you do this many times with many randoms, searching for many random objects, right? That's still in big O of n. Okay, so the hash collections, they can do much better than, they can search much faster than big O of n, right? So on average, under certain assumptions, the hash collections can do a search in O1 time, regardless of the number of elements in the collection, right? So constant time regardless of the size. Conceptually, I'm going to talk about conceptually how these things work. In CISC125, the data structures course, you'll actually see how these things work, or you'll see different variations of these things. So these things are called hash tables. Right? So the easiest way to think of a hash table is it's just an array, right? So it's just like a regular array. So here I have an array of n plus 1, of size n plus 1. Right? Now, in an array, you can hold one element in each array location. Right? So for a hash table, we're going to imagine that each one of these array locations is instead what's called a bucket. So a bucket can just hold multiple items. Right? So each one of these buckets is able to hold 0 or more objects, or references to objects. To insert something into this hash table, what the hash table does, right, I want to insert an object A into the hash table. So what the hash table does, right, not what the programmer does, what the hash table does, is it calls the hashCode method for that object A. Right? It's able to do this because the hashCode method is defined in java.lang.object. Right? And remember that every little o object in Java has every method that's in big O object, right? So every object has a hashCode method. So the hash table calls hashCode on the object, and that tells it which bucket to put the object into, right? So I want to put A into this hash table, so we take A, or the hash table takes A, calls its hashCode method. Hashcode returns an int, right? So it could be negative or positive or 0. What this arrow means is that the hash table takes the int value returned by hashCode, does something to the int value so that it's in the range 0 to n. Right? Exactly what it does is not important for our purposes. Right? In CISC125, you'll see probably several different ways of how you can map that integer value so that it lies between 0 and n. Right? It turns out this is a very important step of the process. Okay, so the red arrow means take the hash code, convert it to a value between 0 and n. Exactly how that works, we don't care. Right? So when the hash table converts this value from A, right, it gets the value 2. So it's going to put A into bucket 2. Right? So A goes into bucket 2. If you want to put a new object into the hash table, right, the hash table takes your object, calls hashCode on it, gets a value, and turns that, in this case, to 0. Right? So B is going to go into bucket 0. Right? For C, it looks like the hash code gets converted to n, so it's going to put it into the last bucket of the table. Now, each bucket can hold multiple items. So it's possible that when you put in D, right, the table asks D for its hash code, then converts that value. In this case, it converts it to n. Right? So it's going to put it in the bucket n. So you can have multiple items in each bucket. Now, ideally, the distribution of elements in a hash table is uniform. Right? So what that means is that in each one of these buckets, there's roughly the same number of elements. Right? Roughly. It doesn't have to be exact. It's roughly. Right? So each bucket holds approximately the same number of elements. Okay, so that's putting things into the hash table. Now, how do we test if something is in the hash table? Well, you just repeat the whole process all over again, right? So if I want to know, is A in the hash table, right? Hash table takes your object A, calls hashCode on it, does something, and turns that value into 2, right? So it knows it has to look in bucket 2 for the element A. So now it goes into bucket 2, right? And it sees there's one element in the bucket. So it takes your object A and compares it to the element that's in the bucket, right? So is A equal to A? The answer is yes. So A is in the bucket. A is in the hash table. Right? Now what about Z? So is Z in the hash table? So hash table takes your object Z, calls hashCode on it, gets an integer value, converts that, in this case, to n. So now it goes into bucket n. Right? It sees that there's 2 elements in the bucket, so now it uses, it calls equals on each element in the bucket. Right? So Z equals C, that's false. Right? Is Z equal to D? Well, that's also false. Right? Are there any more elements in the bucket? No. So object Z is not in the hash table. Okay, so searching a hash table is usually much faster than linear search. Right? So in a well-designed hash table, under certain assumptions, the number of elements in the hash table does not affect the amount of time needed to search the hash table, right? So it's constant time. Now, if you were actually to do the complexity analysis on this, right? If you have n elements in the hash table, right? In the best case, when you go to search the hash table, you look in a bucket and that bucket is empty. Or the very first element in the bucket is equal to the thing you're looking for, right? So that's 0 or 1 calls to equals, right? So that's O1 time. Now in the worst case, there's nothing actually, in a naive hash table, there's nothing preventing the hash table from putting all of the elements into the same bucket, right? So in the absolute worst case, all of your elements are in the same bucket, and now the hash table basically has to call equals on all of the elements in the bucket, right? So that's big O(n) time, right? So O(n) is the worst case complexity for searching a hash table. On average, though, right, assuming this is true, right? So assuming that the elements of the hash table, the distribution of elements in the hash table are uniform, then you're going to find a bucket, and then you're going to look for, you're only going to call equals on a small number of elements, right? The number of elements that are in the bucket, right? And so if the number of elements in the bucket is not related to the number of elements in the table, then that's O(1) time, right? And so the whole goal in designing a good hash table is to make a hash table where each bucket contains a roughly, contains roughly the same number of elements, and the number of elements is small, right? And that gives you your O(1) complexity. Okay, so what's the problem if you don't replace hashCode, right? So if you don't replace hashCode in your class, but you did replace equals, right, then that means you get the object version of hashCode, right? The big O object version of hashCode, right? So what does the big O object version of hashCode do? Well, it uses the memory address of the object to compute the hashCode, right? Uses the memory address of the object, right? Okay. 16. No. Okay, so back to our example here, right? So we had a point P, added it to the hash set, right? Made a point Q that is equal to P, but it's a different point, right? It's a different object, right? New point 2, new point 2, right? So the address of Q has to be different than the address of P, right? Because they are 2 different objects, right? Can't have 2 objects in the same memory location. So that memory address of that is different than the memory address of that. So when the hash table goes to test whether or not it contains Q, right? The hashCode method for Q uses the memory address to compute the hashCode, right? The memory address of Q is different than P, right? That means the hashCode that's computed using P is different than the hashCode that's computed using Q, probably, Almost certainly. Right? So their hash codes are different, and what does that mean? Well, it means the hash table is probably going to look in a different bucket for Q than it looks in for P. Right? So the hash table looks in the wrong bucket, again, probably, and it does not, oh, I don't know why it says comp, does not find the point, even though P equals Q is true. Right? Okay, so what does this mean? It means you have to replace hash code, right? Otherwise, you can't use the hash containers with your newly created type. Right? And so the idea behind hashCode is you're going to take an object and you somehow need to compute an int value corresponding to that object. So what you do is you look at the fields of the object and you somehow compute an int object based on the fields of the object. Right? So that's how hashCode normally works. If you want to know the gory details of how to actually implement this yourself, the hard way, right? You can look at the hashCode notebook, and it actually describes an algorithm that's used, that can be used to compute a hashCode. We're going to do it a little easier in the slides. Okay, so when you implement hashCode, it would be nice if two unequal objects produced unequal hashcodes, right? Because you want to put these unequal objects into different buckets in the hash table, right? So it would be nice if that happened, but it's not required. Right? So in other words, you can have two objects that are not equal, but they produce the same hash code. If you think about it, that has to be the case. Right? There's only a limited number of ints, and hashCode returns an int. Right? If your object has two fields in it, so it has two double fields, right? There are many more combinations. There's many more distinct objects than there are int values. Right? So it must be the case that two unequal objects are going to produce the same hash code. Right, so that's what you're hoping for. You can't do that in general. There is something, though, that is required. Okay? If your objects are equal, right, now remember what the hash table is going to use this for, right? It's going to use this to look for an object. So if two objects are equal, then it had better be the case that they produce the same hash code. Right? So that the hash table can go into the right bucket and find the thing that it's looking for. Right? So if x equals y is true, then the hash code for x must be the same as the hash code for y. Right? Now, what else must be true? Right? So remember, what did the hash table do to put the object into the hash table? Right? It computed the hash code for the object and then found the bucket corresponding to that hash code. Right? So it must be the case, right, that if x doesn't change its state, that x.hashCode always returns the same value. Right? It can't return a random value because that means the hash table is going to put the thing into a random bucket every time. Right? When it goes to search for the object, there's a low probability that it looks in the right bucket. Right? So these two things must be true for your version of hashCode. Right? The first one is the tricky part. Right? If two things are equal, then their hash codes must be equal. Okay. So how might you go ahead and implement this? So here's our point2 class. The fields are double, but it doesn't matter, right? You could technically write hash code like this, right? So you just return some integer value, in this case 1. You could return 0 or -1, right? Why should you not do this? Right? Remember, what is the hash table using the hash code for? It's using it to compute which bucket to look for the object in. Right? This hashCode method says, always look in the same bucket, right? Whatever 1 maps to in the hash table, right? Always look in the same bucket. So it doesn't matter what the coordinates of your point are. When the hash table inserts it into the hash table, it always goes into the same bucket, right? What does that mean? It means when it searches for the object, it has to look for your object in the same bucket, right? If you have n elements in the hash table, all n elements are in the same bucket. It now has to search all n elements, right? So now you've basically got a list. Right? So your hash collection behaves like a list. Instead of O1 search time, you now have ON, right? Don't do that. Okay. So how do I convert x and y into some int value that would be useful for a hash table? Right? You say, well, I don't know, maybe I can add them together like that. Right? So I add the two fields together and then cast it to an int. Right? Again, this is legal. Right? It's better than the previous hashCode method I showed you. It's still not very good. So the reason why this isn't very good is because two different points where their coordinates are similar but not exactly the same will always hash to the same bucket. Right? So when I add the x and y coordinates of 2 points that are slightly different, right, you get a slightly different number. And when I cast that slightly different number to int, it's probably going to map to the same int value. Right? So for example, if you have a bunch of points and they're all inside the square whose coordinates are limited by 1, right, so there's x, there's y, there's 1 and 1. So if all your points are inside that square, at 0.5 and 0.5, right, then all of these have a hash code of 1, right? Add their x and y coordinates together and then it cast to an int, right? So those are all, those are all going to be 0, not 1. Those will all be 0. All of these have a hash code of 1, and that point right there has a hash code of 2, right? And so you can have many, many points inside that square, but they all produce a hash code of 0, 1, or 2, right? So this isn't a good idea either. What you want to do is, given two different values of x, given values of x and y, you want to try to produce some sort of random value, right? And doing that is actually very hard, right? So, right here. So if you generate, sorry, this is an old slide. I don't know if Eclipse still does this. When you generate equals using Eclipse, Eclipse generates hash code for you. Let me just quickly check if I have Eclipse still open. And is it still here? Domino. Where does hash code? Oh, it is here. Okay. Your version of Eclipse might produce something different. So the method that, the hashCode method that Eclipse generates is it starts out with a prime number, and then it starts to multiply that prime number by the fields of your, it starts to add the fields of your class to that prime number and then do some multiplication. And it repeats that for all of the fields. Right? So the Eclipse version of hashCode generates a hash function that is reasonably good some of the time. But it does not yield what are called state-of-the-art hash functions, nor do the Java platform libraries provide such hash functions. Right? Notice the last part of this method of the comment. Writing such hash functions is a research topic best left to mathematicians and theoretical computer scientists. Right? So in other words, leave this up to the PhDs to actually write a good hash function. Right? That's not your goal when you're writing hash code. So what is your goal? Well, it turns out it's pretty easy now. So in modern versions of Java, you can just write this. There's a utility class called objects, big S, big O, little s, objects. Inside, there's a method called hash. You just pass hash all of the values that you want to use in your hash code. Right? So for a point, I want to use x and y, and that will generate a reasonably good hash code implementation. Right? And so that's the way, if you're asked to implement this on an assignment or something like that, you should do it that way. Now, if you're asked to implement this on a quiz, there might be an easier way to do this, right? Or a more clever way to do this. But this almost always works. Okay, there's something you have to be careful about, though, here. Right? So let's go back a few slides and look carefully at requirement number 1. If x equals y is true, then the hash code for x must be equal to the hash code for y. Right? So when you look at this thing here, right, you can conclude that the fields that you use in hashCode, right, must be the same as the fields that you use in equals. Or the fields that you use in hashCode, you have to use fewer fields in hashCode than you do in equals, right? You can't use more fields in hashCode than you do in equals, right? So let's see why not. Whoop, whoop, whoop. Right, so there's my hashCode method, right? Suppose I just wrote this as the following. So instead of using x and y, I just use x. Right? Is this okay? Right? So you ask yourself, well, 2 points are, so when are 2 points equal? Well, they're equal if they have the same x and y coordinate. Right? So suppose I have the point 1, 2 is equal to the point 1, 2. Right? If I compute the hashCode just using x, right, does that satisfy the requirement that if two objects are equal, they produce the same hashCode? The answer is yes, right? If you just use the x component, then any 2 points with the same x component will produce the same hashCode. So that's okay. Okay, so is this okay, right? Now remember, equals only uses x and y, right? If you were to insert some other field up here and use the some other field to compute the hashCode, but you don't use it to compute equals, now you have a problem, right? 2 points are going to be equal if their x and y coordinates are equal, right? Two objects will have the same hashCode if their x, y, and some other field are equal, right? Not just if their x and y fields are equal, right? So this method here will produce a different hashCode for 2 points that are, for 2 points that are, what is going on? Sorry, I got a stuck key on my keyboard. Okay, so this method here, again, it's stuck key, sorry. Where's my, okay. So this method here, right, produces equal hashcodes only if x, y, and some other field are equal for the two objects, right? Whereas equals returns true only if x and y are true, right? It ignores the other field. So you can't use extra fields here in hashCode, or you can't use fields in hashCode that are not used in equals, right? So watch out for that, right? It's not always super straightforward to implement this method. Let me just jump over to Eclipse and I'll show you source. So if you ask Eclipse to generate hashCode in equals, right, that's fine, yes, right? The very first thing it asks you is, what fields do you want to use to compute equals and hashCode, right? And it will use those fields to compute equals and hashCode, right? It won't let you generate a hashCode method that uses more fields than are used in equals. Okay, so that's all I want to say about hashCode for now. Right? It's relatively easy to implement, right? But the thing you have to watch out for is requirement number 1. Right? Okay, so what other methods are useful in our class? Right? Not just our class, but classes, many other types of classes. Right? So we've got, we have toString, right? Generates the string representation of an object. We have equals, test if two objects are equal. Right? Now we've got hashCode, right? Which you know now you have to implement if you've decided to replace equals. There's another method that's useful for value type classes, and that's called compareTo. Now, compareTo is different than toString and equals. Right? compareTo does not come from the objects class, right? It comes from something else. Right? Okay, so compareTo is useful when you want to compare objects for their order, right? In other words, you want to ask, is this object greater than, less than, or equal to some other object, right? So such objects are said to have what's called a natural ordering. Right? And so in other words, if you have two objects, x and y, right, it's meaningful to ask, is x less than y? Right? Of course, for the numeric types, this makes sense. Right? For strings, this makes sense if you want to compare strings in dictionary order. Right? Dates, obviously, you can compare them in chronological order. Right? Now, what about points? Because we're using the point2 class as an example. Right? So there are many different ways you can compare points. One of them might be by their distance from the origin. Right? So if one point is further from 0, 0 than the other point, we'll say it's greater than the other point. You might not want to do it that way either. Right? So if your class has a natural ordering, so in other words, if you want to sort objects of your type, right, then consider implementing the comparable interface. Right? If you do this, then you let users of your class sort arrays or lists, or you can put them into tree sets or tree maps. You can put your type, basically your type becomes sortable. Right? Now remember, what is an interface? So we haven't implemented an interface yet. So this is going to be our first opportunity to do so. Now remember, an interface is just a group of related methods. The methods have no implementation. Right? So it's just their method header. Comparable has only one method in it. Right? So if you go poking around, if you look up the comparable interface in Java, you'll see that it's an interface called big C comparable. Right? It's got the angled brackets here and the letter T here. Right? So this indicates that it's a generic interface. Right? You can specify the type of element that you want to compare. Right? And it has one method called compareTo. Right? It takes in an element of type T, right, and returns an int. Right? So if you got a class like point2 and you want points to be sortable, you can make your point2 class implement this interface. When you implement the interface, your job is to provide a method that looks like that inside your class. Right? So what does compareTo do? It returns this object with the specified object. So it returns this object with T, compares this object with T. Right? It returns a negative value if this object is less than the other object. It returns 0 if this object is equal to the other object. It returns a positive integer if this object is greater than the other object. If the other object that you're comparing to has the wrong type, it'll just throw an exception. You don't have to do anything special here, right, to throw this exception. This will happen for you automatically. All right, so I would like to compare points by their distance to the origin. Inside my point2 class, I'm going to add a public int compareTo method that takes in a point2 object as its argument. So how do I implement compareTo? Well, I want to compute the distance from the origin of this point. Right? So compute the distance from the origin for this point. Right? Compare the distance from the origin for the other point. And then compare the two distances. Right? If this point is further from the origin, I'm going to return a positive int. If this point is closer to the origin than the other point, I'm going to return a negative int. If they have the same distance from the origin, we're going to return 0. Right? Notice that the contract for compareTo doesn't say what int to return. Right? It's just the sign, so negative, 0, or positive. Okay, so to our point2 class, the very first thing we have to do is now state that we want to implement this interface. Right? So what you do is you put in the keyword implements after the name of the class, and then say what interface do you want to implement. Well, we want to implement the comparable point2 interface. Right? I would like to compare point2 objects to other point2 objects. Right? So we're going to implement the interface comparable point2. Right? Once I've said that, I go into the class and I provide a compareTo method. Right? Public int compareTo, whatever that type is there, goes in here. Right? Typically, that type is the same as that type. I'm replacing a method that's declared in this interface, so I can add the @override tag here. Adding the @override tag will force the compiler to test, is this the correct method, right? Is it public? Is it int? Is it compareTo, right? Does that method exist in that interface? Okay. Now compute the distance from the origin for this point, right? So our point is just, it just has an x and a y coordinate, right? So you can compute the hypotenuse of the triangle, where one side has length x, the other side has length y, right? X squared plus y squared, take the square root, right? There's a method in the math library called hypot that does that for you, right? Hypot is a lot better than computing the square root of x squared plus y squared. The problem with computing this x squared plus y squared is that the value of x squared can saturate to infinity. The value of y squared can saturate to an infinity. If you take the square root of that, you're going to get back infinity, right? Even though the distance is not infinite, right? So in other words, there are values of x and y which lead to the result infinity if you compute it using the square root of x squared plus y squared. Hypot avoids explicitly computing x squared plus y squared. It does it in a different way, right? And it avoids giving you back infinity instead of giving you back some other large value, the correct distance, right? So hypot's the best way to do this here. Compute the distance from the origin for the other point, so that's just hypot of other x and other y. And now just compare these two distances, right? So if this distance is greater than the other distance, then I want to say that this point is greater than the other point. I want to return some positive integer, right? So here I can just return 1. It doesn't matter which value you return. It just has to be positive, right? If this distance is less than the other distance, then this point is closer than the other point to the origin. So I want to return a negative int, right? So here I'm going to return -1. Again, can be any negative number here, right? If the 2 points are equidistant, I want to return 0, right? To indicate that they have the same distance to the origin. Right. Okay. You can avoid this if statement, right? So you can avoid the if statement because there's this class called double. And if you poke around in the double class, you'll see that it knows how to compare two double values, right? So double has a method called compare that compares that value and that value. It returns a negative value if that if this value is less than that value. It returns a positive value if that value is greater than that value. And it returns 0 if these two values are the same, right? So compare and compareTo, they're related, right? They are basically the object version of less than, greater than, and equal to, right? So that's the most compact way to implement this method. Okay, so if you go and look at the comparable interface, right, you'll find the compareTo method. The documentation for the compareTo method is a fairly detailed description of exactly what compareTo must do, right? So the contract for, or the documentation for compareTo ensures that compareTo defines what's mathematically called a natural ordering, right? We're not so interested in the mathematical details here, right? What we are interested in is the following. What we are interested in, though, is whether or not compareTo is consistent with equals. Right? Okay, so remember what compareTo returns, right? So it returns 0 if the two objects are quote-unquote equal. Right? So that sort of suggests that compareTo and equals are related to one another. Right? So we say that compareTo is consistent with equals when both of these conditions are true. Right? So if x compared to y returns 0, then x equals y also returns true. right? And similarly, if x equals y returns true, then x compared to y returns 0. So both of these two statements are true. We say that compareTo is consistent with equals. In other words, when compareTo returns 0, equals also returns true, right? They're consistent with one another. So two equal objects both have a compareTo method that returns 0. Sorry, two equal objects, when you compare them, they give you back, you get back 0. Now the funny thing with compareTo is that it does not have to be the case that compareTo be consistent with equals, right? So they look like they're related to one another, right? compareTo looks like it's related to equals. That's not necessarily the case, right? So in other words, you can have a compareTo method that returns 0, right? But equals returns false, right? Similarly, you can have two objects that are equal, but when you compare them using compareTo, you get back a non-zero value, right? And so one of the common mistakes, well, not common, one of the possible mistakes that students will make is that they're given, or they implement some class, they implement equals, and then they use equals in compareTo. Or they implement compareTo, and then they use compareTo in equals, right? You can't always do that, right? So it depends on exactly how it is you are comparing two objects for equality, and how you're comparing two objects for greater than or less than, right? Notice that this, for points, is not consistent with equals, right? This tests if 2 points are the same distance from the origin, right? If they're the same distance from the origin, then compareTo returns 0, right? So remember what the definition of a circle is. Right, so for a circle centered at the origin, right, that's the set of points equidistant to the origin. Right, so our compareTo method returns 0 for all of those points, any 2 points on that circle. Right? But our equals method only returns true if the 2 points have exactly the same coordinate, right? So that is not consistent with equals. Oop, boop, boop, boop. Right? And so here we have a case where x compared to y returns 0, but x equals y is false, right? It's relatively easy to come up with examples for this. It's harder to come up with examples for the second one, right? And so I will leave that as the exercise for the student to try to come up with examples for the second one. All right, so when you implement compareTo, at some point you're going to compare two values, right? So if you're comparing values of type float or double, so if you're comparing floating point values, right, use float compare or double compare to do the comparison, right? If you're comparing ints, then you can just use less than or greater than if you want to. You can also use integer.compare or long.compare. I guess short.compare if you're using short values. Okay, so what happens if your compareTo method is broken, right? So it's incorrect in some way, right? Then anything that relies on compareTo is also broken, right? So tree set and tree map, those are the collections that sort their elements, right? So if you're using your type and putting it into a tree set or using it as the key for a tree map, these two collections will probably behave incorrectly, right? The sorting of the elements will probably be incorrect. Any method that any method that requires that your collection be sorted is probably also broken, right? So for example, binary search requires that the elements of your array or list be sorted, right? If compareTo is busted, then binary search is not going to work properly on your collection either, on the collection of your elements either. right? So anything that assumes something is sorted, probably not going to work properly if your compareTo method is broken. Okay, so what about that int value that's returned, right? So in our previous example, we're just returning -1, 1, and 0. Every once in a while, so very occasionally, right, you can cook up a compareTo method where the returned value is useful, right? Is useful for other than just comparing, right? So for example, the compareTo method for counter. So I'd like to compare two counters, right? It's easy, right? You just compare their values. Right? So remember, for the counter class, it's got some field called value, right, that represents the value of the counter, right? You can implement compareTo so that it returns the difference between the two counters, right? So if your counters are off by, if compareTo returns -1, you know the count for this counter is 1 less than the count for the other counter, right? That might be useful in some examples, right? So you could write, in this case, return this value minus other value, right, which is just the difference in the counter values, right? If you find yourself writing something like this, right, you have to stop and pay very close attention to what you just wrote, right? For the counter class, this is correct, right? Why is this correct for the counter class? Because the counter class has a promise in it, right? It has an invariant, right? Value is always 0 or positive, right? The fact that it's always 0 or positive means that that result cannot overflow, right? If you have a field that doesn't have that restriction, right? In other words, value can be any int value, right? That thing there can overflow. And if it overflows, the sign of the result is wrong, right? And your compareTo method is busted, right? Be very careful writing the difference of two values, right? It almost never works the way you want it to, right? It only works here because the value is 0 or greater, right? And the class is implemented in such a way such that that's always true, right? So every once in a while, you can return something useful in the return value for compareTo, right? The string version of compareTo tells you the difference between the two characters, the first character that differs in two strings. All right. Any questions about hashCode or compareTo? Yes. Go ahead.
Sure. I was just sort of curious. In the hash table, there's the value of n. I was just wondering what that depended on.
Oh,
Like
the size of the hash table. That's a good question, right? So there's if you sit here and think about what the hash table is trying to do, right, you'll quickly realize that if you have many elements in the table, right, that value of n is probably going to have to be quite big, right? If you stop and think about it a little longer, right, and you ask yourself, well, how am I building the hash table? Well, it probably starts out at size 0, right, and then you add a bunch of elements to it, right? And so that size n here is not fixed, right? As the hash table, as you add elements to the hash table, occasionally the size of the hash table will have to be resized, right? When you resize the hash table, that becomes an expensive operation. You basically have to rehash all the elements in it. Yeah. So that's a good question. Yeah, there's lots and lots of details about hash tables that this completely overlooks, right? And even your CISC125 course, you will not be taught how to implement a really robust hash table, right? There's just a lot of stuff that you need to know. Any other questions? All right, super. See you on Wednesday.